For hundreds of years, people have tried to make perpetual motion machines or engines. These are engines that will run without any input of fuel. They'll run forever. The people who have tried to make such machines sometimes are those who want to try out a new idea, and sometimes they are frauds who want to fool other people. The fact is that the second law of thermodynamics, which is going to be the subject of this lecture, tells you that this simply cannot be done. We're also going to talk about the most efficient possible machine that can be made and which is allowed by the laws of physics, that is the Carnot engine. It may not be a machine that is easy to make, but it is a fascinating example of something that is created by the mind and which we can only hope to work towards. Before we move to our discussion of thermodynamic engines, let us remind ourselves about the nature of heat. Well, of course, heat is a form of energy, but it's a very particular form of energy. That energy comes from randomized motions of the constituents. Those constituents can be atoms or molecules or quarks or gluons or whatever, but on the average, their momentum adds up to zero. So this object over here can be at rest, but it can have a lot of energy if the constituents are moving rapidly enough. On the other hand, if those constituents are moving in one direction, then the whole object has got kinetic energy, but it could be very, very cold and could have no heat or thermal energy. So heat is randomized energy, whereas kinetic energy is organized motional energy. We're going to define a thermodynamic engine, or you could call it a heat engine, as being that which converts heat into mechanical work. It could also convert work into heat, but it has to be done through a cyclical process, which means that whatever state that heat engine started out with, it returns to that state at the very end of the cycle. So, suppose you started with a certain pressure and a volume and a temperature, then as you go through the various processes within the engine, you will ultimately end up at the same pressure, volume, temperature, or whatever. In this process, work is done. That work is P/dV, and if we add up those little bits of work that are done as we go around the loop, then that is the integral of P/dV. This integral has a loop which signifies that the initial point and the final point are the same. Of course, the engine must always respect the first law of thermodynamics, which says that the change in the internal energy, delta U, has to be equal to the amount of heat that you put in. So this could come from, let's say, burning fuel, minus the work that is done by the engine. Now U, the internal energy, is a state function that depends upon P and V and T. And so when you come back to the original position, the net change in delta U has to be zero. So obviously, that says that delta W and delta Q have to be exactly the same. Let me denote a general thermodynamic engine of any kind with this circle over here, with this X. Now, according to this, whatever heat flows in is converted into work. And I stress over here, this is the net amount of heat that comes in. So in actual fact, some heat could come in and some heat could go out. The net heat is the incoming heat minus the outgoing heat. Historically, thermodynamics was developed at a time when heat engines like this, the steam locomotive, were being developed. So you can see that the coal provides the incoming heat, and here from the exhaust is the waste heat. The work, or you could call it the useful work, is that which this locomotive does in pulling the train along. Well, now we have more sophisticated engines, but the idea is the same. You burn some fuel that provides the heat, some waste heat comes out of the exhaust, and the useful work is that which the engine delivers to the tires. The general idea behind all thermodynamic machines is that there is a high temperature reservoir and there is a reservoir at low temperatures, so this could be the environment to which the waste heat is thrown out. We denote the amount of heat that is taken from the high temperature reservoir as QH. That flows into the engine, whether that engine is this or that. Work is done, and the waste heat flows out into the low temperature reservoir, which could be the atmosphere. So by the first law of thermodynamics, the amount of useful work that is done is equal to the net heat, which is the heat taken at high temperature minus the heat rejected at low temperature. Here H means hot and C means cold. But let's not think that thermodynamic engines are restricted to the things that we make. In fact, there are thermodynamic engines in nature as well. Here is a model of the Earth's atmosphere which can be modeled as a thermodynamic engine as well. So, heat from the sun is absorbed by the Earth's surface, more at the tropics and less at the higher altitudes or the extra tropics. And, of course, some is reflected back. However, the net amount of heat that is received in the tropics is greater than that at the higher altitudes. And so the surface temperature here is larger than the surface temperature here. So again, we have a situation where we have a high temperature reservoir and a cold temperature reservoir. Between these two reservoirs, there operates a heat engine. That heat engine does work in the sense that it moves air from here to here. This is a way of understanding some aspects of atmospheric physics. As yet another example is a refrigerator, the ordinary household refrigerator, which takes heat from whatever is inside, so that's the cold reservoir, and it expels heat into the environment. And so that is the high temperature reservoir. But this can't happen by itself. The electric motor inside this refrigerator has to do work. And so one must supply work over here in order to move heat from inside the refrigerator to outside. You could say that this is a heat engine which is operating in reverse. Many of the principles of thermodynamics were discovered by Carnot, and in particular, we will spend some time understanding the Carnot engine, which is a reversible thermodynamic engine. Again, you remember that a reversible thermodynamic system is that which is in equilibrium at every point. This engine uses some working substance. That substance could be either a gas or it could be a liquid. Now, in the first part of the cycle, the working substance, gas or liquid, expands isothermally from the point A to the point B. Isothermal means that at every point the temperature is constant. That constant temperature is the temperature of the reservoir. So at every point along this path, the temperature is equal to the temperature of the hot reservoir. So obviously TA and every point over here, including TB, are equal. Then from point B to point C is an adiabatic expansion. Adiabatic means that no heat is allowed to enter or leave the engine. Then from point C to point D, we follow a path which is again isothermal, but this time it is compression. So on this path the volume was increasing, now on this path the volume is decreasing. Once we reach the point D, then adiabatic compression takes place. So again, no heat is lost or gained on this path, but now the volume is decreasing, as you can see, whereas earlier it had been increasing. Here's a picture by which you can understand this better. So suppose that this is the working substance, gas or liquid. You supply heat to it from the hot reservoir, and so there's a pressure that moves this piston up. The piston is doing work, obviously. Then you disconnect it from the reservoir, and so no heat is allowed to enter or leave the system. So this is the second phase. In the third phase, the piston compresses the gas, and an amount of heat, Q cold, is thrown out as waste heat. Finally comes the adiabatic compression. So the piston moves, compresses the gas, and we arrive back to the initial point A. Make sure that you understand this. Between A and B, heat is taken in, and that amount is QH. Between C and D, heat is expelled, and that amount is QC. But on this path and on this path, no heat enters or leaves the system. However, work is done on every segment, this, and that, because the volume keeps changing. Let's define eta, the efficiency, as the total work that is performed over one cycle divided by the amount of heat that is absorbed. Well, from the first law of thermodynamics, as I've just argued, that amount of work, we called it delta W, is QH minus QC. When we divide by the amount of heat absorbed, well, that heat absorbed is QH. And so eta is this quantity, 1 minus the amount of heat expelled divided by the amount of heat put in from the hot reservoir. Of course, if QC was 0, if no heat was expelled, if there was no waste heat, then the Carnot engine's efficiency would be 100%. The Carnot engine is very important in thermodynamics. You can ask the question, has anyone ever built a Carnot engine? Answer is no. Why not? Well, there are at least two good reasons. First of all, a Carnot engine has to be a reversible thermodynamic system, which means that you have to do things very, very slowly. And in fact, to go from this situation to this situation to this, and come back to this, or looking over here, to go around this path, would take an infinite amount of time, theoretically. Of course, actual thermodynamic equilibrium is established after a few atomic collisions, and so one really doesn't need an infinite amount of time. A few microseconds could be enough, for example. But that's not the only reason why a Carnot engine has not been built. A Carnot engine also requires that there be no friction. So this piston over here, as it moves up, should have zero friction. So therefore, there's no such thing as a Carnot engine in actual practice. Then you can ask the question, why do we waste so much time studying the Carnot engine? why is it so important? And the answer is because we can gain a great deal by studying free particles in classical mechanics, and we can gain a great deal from studying the Carnot engine in thermodynamics. They are both abstractions, but abstractions is what physics thrives upon. Let's now come to something that's absolutely fundamental, the second law of thermodynamics. There are many ways by which this law can be stated. One is by Lord Kelvin. His statement is that heat cannot be extracted from a reservoir and converted entirely into work. So Kelvin is basically saying that you need at least two reservoirs to run an engine, a hot and a cold reservoir. Another way of expressing the second law of thermodynamics comes from Clausius. According to Clausius, heat cannot go from a reservoir of lower temperature to a reservoir of higher temperature. Basically, he's saying that heat can't flow from a cold body to a hot body by itself. By itself means that you have to do something else in order to make heat flow from a cold body to a hot body. Now, from the Kelvin statement, the efficiency of any thermodynamic engine must be less than 1. Remember, he's saying that you cannot convert heat entirely into work, and efficiency is defined as the work done divided by the heat put in. So obviously, eta is less than 1 according to the Kelvin statement. Now, these two statements here appear to be very different, but in fact, they are exactly equivalent to each other. And this is now what we shall establish. So, suppose that Kelvin is wrong. Then the energy produces no waste heat. It is 100% efficient. In terms of pictures, what that means is that heat is taken from the hot reservoir and converted by this thermodynamic machine entirely into work. There is no waste heat that flows into the cold reservoir. Now suppose that I take the work that is done by this engine and use that in another engine, which then takes heat from the cold reservoir and puts it into the hot reservoir. Now, these two can be made at the same temperature, in which case what has happened is that heat taken from the hot reservoir has then taken heat from the cold reservoir and moved it to the hot reservoir. So, if Kelvin is wrong, then Clausius is also wrong, because contrary to what he said, heat has indeed flowed from the cold to the hot. Now suppose Clausius is wrong. Then heat can flow from the cold to the hot reservoir all by itself. Okay, let's then take a second machine. Then that machine takes heat from the hot reservoir, converts it into work. Now, imagine the following. Suppose that these two hot reservoirs are at the same temperature, and these two cold reservoirs are at the same temperature as well. So, the heat Q which goes up then gets returned over here, in which case this hot reservoir is not playing any role at all. So therefore, you could imagine that this heat is going directly into this machine, and this reservoir does not even need to exist. So in fact, what has happened is that from this cold reservoir, remember there are only one now, net work has been produced. But if that is so, then Kelvin is also wrong, because work is produced using one reservoir only. So, to summarize, the Kelvin and the Clausius statements are exactly the same. If Kelvin is wrong, then Clausius is wrong. If Clausius is wrong, then Kelvin is wrong. And so, the two are exactly the same. Let's now use the second law of thermodynamics to derive some very interesting consequences about the Carnot engine. In fact, this Carnot engine is universal. What that means is that whatever Carnot engine you make, so whatever its shape, size, the nature of the hot and cold reservoirs, or whether you use a liquid or a gas, and whether that gas is an ideal gas or not, in every case we'll be able to see that the Carnot engine has universal characteristics. To prove this, let's take a hot reservoir and a cold reservoir, use this engine, and this engine can be any engine. It can be a non-reversible engine, not necessarily a Carnot engine. So, this engine takes in heat Q1, expels heat Q2. The amount of work that it does is the difference of the two. Now, between the same two reservoirs, we have a Carnot engine. But this Carnot engine will be operated in reverse, which means that we are going to give it work. We're going to put in work and pump heat out from the cold reservoir into the hot reservoir. So this is just the Carnot engine that we talked about, except that all the arrows have been reversed. So this is going in instead of coming out. This is going out instead of coming in, and same for here. Now let's do a little bit of bookkeeping. So we're getting energy W out from here. That W is Q1 minus Q2. And we're putting in work W prime. So the net amount of work that we're getting out is W minus W prime, which is simply this. Suppose I choose Q1 equal to Q4. That means the heat that's coming in over here is equal to the heat that's going out over there. In that case, the net amount of work is simply Q3 minus Q2. But we've just heard Lord Kelvin say that work cannot be extracted from a single reservoir. You need two reservoirs. But look, over here, this is essentially one reservoir because the same amount of heat is being extracted as is being given back. So you can just remove this reservoir, and so we have one reservoir only, just the cold reservoir, in which case the work has to be zero or a negative quantity. So this work is less than or equal to zero, which means that Q3 has to be less than or equal to Q2. We talked about engine efficiency earlier. That was the ratio of the work that is extracted from the machine divided by the heat that is put into the machine. And so the engine efficiency for X is simply the work, which is Q1 minus Q2, divided by the heat that is put in Q1, and that's eta X, which is 1 minus Q2 over Q1. Well, we can do exactly the same for the Carnot engine, and here, if you simply reverse all the arrows, the efficiency of the Carnot engine is then simply 1 minus Q3 over Q4. But since we have chosen Q4 and Q1 to be the same, it's equal to this quantity. However, you see that Q3 has to be less than or equal to Q2, and so that says that eta C has to be bigger than or equal to eta X. In other words, we've come to this remarkable conclusion that the Carnot engine is the most efficient engine possible. That's because we've compared it with an arbitrary engine, X. But of course, we could have chosen X to be the same as C. Then let's put X equal to another Carnot engine. So eta C then has to be greater than the efficiency of C prime, but also the efficiency of C prime has to be greater than the efficiency of C. So obviously there's only one solution, which is that the two Carnot engines are equally efficient. In other words, this is a proof of universality. It doesn't make any difference as to what that Carnot engine is made of. Let's now analyze the Carnot engine, but now assume that the working substance is an ideal gas. That makes it possible to do the calculations easily. So, to remind you, here is the situation. This isothermal expansion, adiabatic expansion, then isothermal compression, and then finally adiabatic compression. Let's see how much work is done in going from A to B. Well, actually, we've already calculated this in module 1.4, and we found that the work done in going from here to here is R times T. Remember, there's only one temperature. This is all at temperature TH into the log of the volume here at the point B divided by the volume at the point A. So this came from using PV equals RT. And remember, we're considering only 1 mole of gas, so N is equal to 1. What about the amount of heat that we had to put in? You remember that for an ideal gas, the internal energy just depends upon the temperature. And so the internal energy here and the internal energy all along, including here, remains constant. Since there's no change in internal energy, therefore, the heat put in is exactly equal to the amount of work done, and so QH is this quantity. Now let's go to this segment over here. How much is the work done in going from B to C? This will require a little side calculation. Actually, I've already done this in module 1.5 in the solved example, but let me repeat it for completeness. So we know that the work done is P dV. We go from the point B to the point C, which means we go from the volume VB to the volume VC. Let's recall that this is an adiabat. For an adiabat, PV to the gamma is equal to a constant, and so P is equal to CV to the power minus gamma. You put this into here, and immediately you get this result. So you add 1 to the numerator, and minus gamma plus 1 comes in the denominator. But then we can simplify this because V to the power minus gamma is equal to P divided by C, and that C will cancel over here. So this becomes this. We have PV at the point C minus PV at the point B. And now remember that PV is RT and gamma is the ratio of the specific heat at constant pressure divided by the specific heat at constant volume. Simply put that in here and you get this factor is equal to minus CV divided by R. Now PV minus PV, let's use the ideal gas equation again. So the R will cancel and we get our final result that this work WBC is equal to CV into TB minus TC. I'm going to put this into this. So now let me clear some space and go here. Of course, no heat flows in or out during this segment from B to C, and so QBC is 0. Next, let's calculate how much work is done in going from C to D. Of course, we're not going to repeat the calculation. It's now pretty obvious. You just take the ratio of the final to the initial volumes, take the log and multiply by RT. And in this case, the temperature is Tc, that is T of the cold reservoir. By the same reasoning as for the upper segment, there's no change of the internal energy here, and so the amount of heat that was expelled was RTC log Vd over Vc. Now, there's one important thing to notice over here. You see that Vb is bigger than Va. That's obvious from here. This has been an expansion, and so QH is log of something that's bigger than 1. Therefore, QH is a positive quantity. So this is the amount of heat that you actually put in. On the other hand, there is compression over here. So Vd is less than Vc, which means that this is a quantity less than 1, which means that Qc is going to be negative, and that makes sense because Qc is the work that was put into the machine by definition, and so it should be negative because a negative value corresponds to expulsion of heat, waste heat. Finally, let's look at the D to A segment. We don't have to redo this calculation. You can see that the work done in going from D to A will be CV into TD minus TA. Again, this is an adiabat, and so no heat was gained or lost. If we look at the total amount of heat that's absorbed, that's just what you get from the segment AB. If you look at the amount of heat that's wasted, well, that's just in this segment over here. Let us now look at the total work output. So add up the work done on all the segments A to B to C to D to A, and that's this. Let's look over here. WBC is this, TB minus TC, whereas WDA is TD minus TA. As you can see, this over here is an isotherm. And similarly, TC and TD are equal. So if you add up WBC and WDA, that sum is equal to 0. So the only work that is done is on this segment and on that segment. In the first segment, we have log of VB over VA. In the third segment, we have VD divided by VC. But is there any relation between this and this? Of course there is, because this gas has expanded adiabatically from here to here, and we know that for adiabatic expansion, PV to the gamma is a constant, or you could say TV to the power gamma minus 1 is a constant, and so whatever its value here, the same value exists over here. So we have these two relations, one for the BC segment and one for the AD segment. And of course, recalling that TA and TB are the high temperature reservoir and TC and TD are the low temperature reservoir temperature, this immediately tells us that this ratio, VB to VA, is equal to this ratio, VC divided by VD. Now use the fact that log of x is equal to minus log of 1 over x, and so we have this relation. This means that if you add WAB and WDA, then you simply get the total work done. Remember that this and this had cancelled, so the total work done is proportional to the difference in the temperatures of the hot and the cold reservoirs. Now we can calculate the efficiency of the Carnot engine, which is the work performed divided by the heat absorbed. And this is the work performed, and the heat absorbed is QH. QH is given here, which means now the logarithms cancel and we get this extremely important and useful result, which says that the efficiency is 1 minus the temperature of the cold reservoir divided by the temperature of the hot reservoir. This is an extremely important result because we've already proved that the Carnot engine is the most efficient engine possible. The formula that we've used for the efficiency is the same that we used just a little while ago, where it was 1 minus QC divided by QH, and QC is this, QH is this. So you note that QH and QC are proportional to the respective temperatures. This fact remains true whether or not the working substance is an ideal gas or an actual real gas. Finally, I'm going to solve an example. Here there is a reversible engine which uses an ideal gas. That gas has specific heat Cp at constant pressure. So the ideal gas is its working substance. This is not a Carnot engine. Here the cycle consists of 2 segments at constant pressure and 2 adiabats. So from here to here, you go at constant pressure pH. Then from B to C, you go on an adiabat. From C to D, the pressure is again constant, but at a lower value PL. And then there is a second adiabat in going from D to A. We are asked to find the efficiency in terms of the high pressure and the low pressure. Also, we are asked where on the cycle A, B, C, D is the temperature the highest. And finally, we are asked to compare the efficiency of this engine with a Carnot engine. Let's go through the same procedure. So in going from A to B, now we're not going at constant temperature, we're going at constant pressure, and that makes it much easier because the work done is integral P dV, but P is a constant, so you pull it out, you get pH, and then you get the difference in the volumes, VB minus VA. Much easier. How much heat did you have to put in? That was QH. That was simply the specific heat, and this is at constant pressure, multiplied by the difference in the temperatures. And so this is just using the definition of specific heat. Let's now go to the second segment from B to C. Here, the work done in going from B to C is what we've already calculated in the case of the Carnot cycle, because this is just the adiabat. As you travel along the adiabat, the total amount of work that is done is CV into TB minus TC, exactly as before. And since this is an adiabat, QBC is 0. Next, we'll go from C to D. Again, this is perfectly straightforward. It's just like here. There's the pressure into the difference of the volumes. Just remember that here VB was bigger than VA, and so WAB will be positive, WCD will be negative. As for the amount of heat that you put in taking the gas from C to D, well, that's Cp into the difference of the temperatures, exactly as here. The final segment, going from D to A, the work done is Cv into the difference of the temperatures. Again, this is an adiabat, QdA is 0. Now let's calculate the efficiency, eta, which is 1 minus the amount of heat expelled, divided by the amount of heat that's put in from the high temperature reservoir, and we've calculated everything now. QC is just TC minus TD, and QH is TB minus TA. The CP's cancel. Now let's use the ideal gas equation. PV is equal to RT. So T gets replaced essentially by PV. P is constant on the segment A to B. For this, TC minus TD, which is here, we have PL. And for TB minus TA, which is here, we have pH. But of course, these volumes are not independent of each other. From here to here, we travel on an adiabat, and from here to here, we travel on an adiabat. So PV is equal to a constant that holds true for this segment and for this segment. In fact, exactly as for the Carnot case, we find that VB divided by VA is equal to VC divided by VD. And so we get our final result that the efficiency of this engine, which is not a Carnot engine, is 1 minus the low pressure divided by the high pressure to this quantity over here, gamma minus 1 divided by gamma. So I've just left out half a step for you to fill in. That little bit you should do using this, and PV equals RT. Now let's go to the second part, at which point over here, A, B, C, D is the temperature the highest. Let's see. From PV equals RT, obviously TB is bigger than TA. So look over here, the pressure is constant, and so the temperature is proportional to the volume. T is proportional to V, which means that as this gas expands at constant pressure, the temperature goes up. Equally, as this gas gets compressed, squeezed into a smaller volume, its temperature has to decrease. So obviously we have this relation that TB is bigger than TA and TC is bigger than TD. But what about over here? B to C. We see using this adiabatic equation, and remember that gamma minus 1 is a positive quantity, and so we finally conclude that TB is the highest temperature. Unfortunately, I have run out of space and time, and so I leave this very last part. Find the efficiency of this engine and compare it with a Carnot engine. Of course, what you will find is that the efficiency will be less than that of a Carnot engine. Good luck in proving this.